Thanks, David, for the introduction, and thanks to the organizers and for the Institute for hosting this workshop. And I want to tell you about ranks of tensors, more precisely asymptotics of ranks of tensors. And I on purpose didn't say tensor rank, but ranks of tensors, because there are many choices how to choose your rank. And I want to just start by saying that I don't have that many slides actually. So there's time, feel free to interrupt. David, just feel free to relay questions. I can't see the chat now while we're speaking, but I have all of you. So I actually have two monitors, so I have all of you as well. So if you want to, you can also wave at me if you want to take your, camera on and wave and say, I have a question here or something like that.
I will also monitor the chat.
Interactive if you want. If you want, we can make it interactive. I get a blackboard behind me, so I can draw something for you on the blackboard. Anyway, so let's get started. I'm here in Copenhagen in Denmark. It's late afternoon. It's turning 6 p.m. now. The sun is slowly setting. It's only setting around 10:30, 11 p.m. at night. Yes, it's one of the few days I'm actually in my department. Because I'm still kind of at home, although Denmark has been sort of not too harshly hit by the pandemic. The research I'm doing is funded by the European Research Council, by a European project, and then by the Innovation Fund Denmark. And more importantly for us directly here by the Velux Foundation. This is a foundation funded by window producers, so the windows and slanted roofs you might know are from a foundation, are from a company called Velux, and a large pharmaceutical company, Novo Nordisk Foundation. All right, asymptotics of ranks of tensors. What is this about? Let's get going. I want to start with the definition. So you pick your favorite field, F. I usually pick the complex numbers. Then you have to pick an order of a tensor, like a dimension, sometimes it's called, but let's call it an order of the tensor. So I usually pick k equal 2, that's like the matrix case, or I pick k equal 3, but you can pick a higher k if you want. Then you should pick a number d, I call it number d. It's kind of like the size of your matrices. I call it D because I call it dimension, but that sometimes is confusing. But it's usually not so, the D is not so relevant for this talk as long as it's large enough, okay? Most of the time, it's fine if it's large enough. Now, what is a tensor? I define a tensor as an element in the k-fold tensor product of Fd. Okay. Let's do two examples. K equal 2, that's the matrix case. I brought you the unit matrix, 1, 0, 0, 1. And I brought you the unit tensor in k equals 3 here. This is a cube, 2 layers. Okay? It's just to bring us on the same page. Okay, everything clear? I think it is. Let me do a poll. How many people have not picked the complex numbers as their favorite field? Now I want to introduce a notion of restriction, and I don't know if it's implemented in Tensorly, but I hope it is. You pick two tensors, t and t prime. Okay. And now we introduce this notion. We're going to say t restricts to t prime, and I'm going to write t larger equal to t prime. That's the case. If there are matrices a1, a2 up to ak, such that A1 tensor A2 tensor AK applied on T gives T prime. Okay? So in other words, if I can, I would say massage the legs of the tensor. Okay, you do a linear transformation on the legs of the tensor, on these K legs of the tensor, and then you get another tensor T prime. If that's possible, then you say T is better than T prime. T restricts to T prime. Okay? T is like stronger. That's why it's bigger equal to T prime. Okay, here's an example. Okay, so the unit matrix is bigger or equal to 1, 0, 0, 0. Well, why is that? Because what I can do is I can apply the matrix A1. Can you see my mouse actually?
Yeah.
Okay, so I can apply, for instance, on the second one, I apply just the identity. A2 is the identity, and A1 is just the 1, 0, 0, 0. And then if I apply it, of course, the identity is not doing anything, and then I'm just left with this matrix. Again, it was a very simple example. I'm sure you can cook up more complicated examples. I struggled here. I wanted to do this here. This unit tensor, I wanted to restrict to the unit matrix embedded as a tensor. Can you see this? The one from behind moved forward. Okay, so I struggled doing this in here, but here is how you do it. Okay, so you basically apply these three matrices. Okay, you can apply these three matrices, and you see it's like identity, identity, and then here you have to do this non-trivial matrix. And then if you apply it, the one is moving forward. Okay, so in my quantum information world, we're going to say that you would say that the Greenberger-Horn-Zeilinger state has been transformed into an Einstein-Podolsky-Rosen state. But this is sort of like our local lingo. But it's really the unit tensor that was converted into a unit matrix here. All right. Now, some more operations. I can do direct sums on tensors. Okay, so I can take t and t prime, and I can put them basically diagonally up here. Okay, I brought this for you, right? So you take a matrix, a blue matrix and an orange matrix, and you put them diagonal in a diagonal matrix. That's a direct sum. Or you can take them in a tensor, you put them in the diagonal of the tensor. Okay? That would be the corresponding direct sum. The direct sum is kind of like good now to introduce the unit tensor of size d. So that's just the diagonal. So if you were to take the 1 by 1 matrix with the 1 in it, and you direct sum it d times, then what you're going to get is this diagonal. And I'm going to introduce this symbol here. These are not is not quantum mechanical notation. It's really tensor notation. With these, I don't know how to call them, these pointy brackets. All right, here we go. We can also do tensor products with tensors. So you take a tensor t and a tensor t prime, and then you tensor them together. And then you could imagine that you get a tensor that has order 2k, but actually what we're going to do is we're going to group them. Okay, so we're going to make a tensor. This is the Kronecker tensor product. So the outcome of it is actually again a tensor of order k. So we preserve the order of the tensor when we do this Kronecker tensor product here. I brought you an example. So I'm from, how do I do this? If I switch off my camera, video, you see the symbol for our center here for QMath in Copenhagen. And so I took the tensor product with it, with this little 2 by 2 matrix here with these colors in. Okay, so blue, black, green, and orange. And I took the tensor product, and what happens is, of course, that I get this big block matrix, and the Q just appears in these different colors. Thought it was kind of cute. I can also take this diagonal tensor here, and I can tensor it with a 3D classes. And then what happens is the 3D classes appear in here. Okay. But now, interestingly, actually, you can also do it the other way around, and it looks a little different. Right? If you do this and you tensor it with this, you get that. And of course, you could take a proper tensor here, not the diagonal one, but anyway. Okay, so I guess it illustrates a little bit what the tensor product does. Now there's a very nice, on matrices, there's a very nice function. It's called rank. It's matrix rank. It's really very nice. It's monotone. That means it's not increasing under restriction. So for instance, here is an example. So the unit tensor, the unit matrix has rank 2, and then you restrict it to something has rank 1. So it doesn't go up. It actually went down in this example. The rank is also nice because it's additive under direct sum. So the rank of this direct sum is actually the rank of the blue part plus the rank of this orange part or brown part. And then it's even more surprising is that it's multiplicative under the tensor product. So the rank of this is actually the rank of the first one times the rank of the second one. And these are all really nice properties of rank. And then there's another very important property that very often one forgets. It's normalized. Namely, that if I compute the rank of the unit matrix, it's actually the size of this unit matrix. So it's D. That's kind of an important property. Now, if we go to tensors, in the old days in the entanglement world I was living, maybe still partly living, I was thinking of entanglement, zoo of entanglement measures. So now that I prepared this talk, I was thinking of the rank zoo. There's many different notions of tensor rank, and we have seen multiple already in the previous talk. In the previous talk, two notions were, for instance, the dimension, the bond dimension of a matrix product state is a notion of rank in some sense, and then there is also the notion of the actual rank in like a power factor decomposition. But so here is the rank zoo. I brought you the tensor rank. Here is my favorite definition. The rank of a tensor T is the minimum R such that the unit matrix or unit tensor of size R restricts to T. It's maybe a little bit of an unusual way of defining the rank, but trust me, it's equivalent to the one that you know, and I wrote it down for 3 factors here because it was fast to do. It's the minimum of R such that I need R product states or product tensors in, or I think simple tensors they're called. Yeah, I need R simple tensors in order to write T as a sum of them. Okay, so this is the standard way, and it's very easy to see actually that it's equivalent to this way. Why is it? Because I can just from a unit tensor, I can just change the components locally into the alpha I and beta I and gamma I require for the decomposition. Okay, I'm sure you all have seen of tensor rank. There's another beast that's kind of like a mouse. It's the subrank. It's often much smaller than the tensor rank, but it's equally nicely defined. It's actually the maximum of what you can get when you want to out of your tensor. How many unit tensors can you get out of your tensor? Okay, so start with T. How much R can you distill from it? What's the maximum possible? And this is also a very nice function. It's usually called Q of T here, the subrank. And it's easy to see that the rank is bigger than the subrank, but you see now the symmetry. So Volker Strassen actually said the rank is the rank of a tensor is somehow the cost of it, right? This is how much a unit tensor have to pay for the tensor, but the rank is the value of it. So it's how much I get when I want to sell it again. But there's a lot of different ranks in between, and I put them into 2 categories for our maybe the people more from the algebraic from the algebraic geometry community are very familiar with those. There is, for instance, the border rank, sort of like taking limits. There's the smoothable rank. It's also kind of taking limits. There's really weird things like the cactus rank, this is of course a beast that we've seen also in the previous talk. It's the flattening rank. So it's basically you make a matrix out of it. And I say now here the maximum of the flattening ranks because you have of course different options of making flattenings. And I want to put in this category of rank functions the maximum of them, because somehow these are all similar in spirit. And then there is another group of ranks. For instance, you could take the minimum of the flattening rank, and then there's a bunch of other ones. There's a slice rank. Tens Tau has been working on this. There's geometric rank. There's a partition rank. There's analytic rank. There's all sorts of other ranks. And I put them into these categories, and I'm sure you have maybe your favorite ranks. But what I want to say is that these guys here, they're more like tensor rank, and these guys down here, they're more like subrank. And used maybe in order to understand. So these are maybe often used in order to understand something about tensor rank, and these are maybe often used in order to understand something about subrank. So they're basically, you can think of them also like tools. But there's also like crazy creatures like symmetric rank. If you are dealing with symmetric tensors, I'm sure you have your own favorite animal of a rank. Actually, I can make it interactive. Anyone wants to add a rank to my slide? What have I forgotten? David, please. Oh, someone wants.
It's not likely to forget something. I think this is a complete
No, I don't think it's actually complete. I was already notioning this bond dimension thing is also ranked.
Cactus border rank has been proposed by Joseph Landsberg. The cactus border rank.
Yeah, of course. You can make border out of this here, right? You can make like cactus bordering, smoothable bordering. Yes, absolutely. Good point. Very good. More things here. Anyway, yeah. Joseph, did I forget anything from this category here? I think I did.
Border subrank has been mentioned by Peter Burgieser. Border subrank has been mentioned.
Border subrank. Yes, very good. Yes, okay, excellent. Good.
Oh, G-stable rank.
Oh, G-stable rank. Yes, very good. More stuff. What's your favorite?
Okay, yeah, warring rank was brought up again, but this, of course, is already on the slide, as the poster has now noticed.
My favorite rank is Slater rank, by the way, so it's not even on the slide. So what do they have in common? What do they have in common? Anyone? I have a few things. Well, they're monotone, they're normalized, very nice. But actually, I think they're all not multiplicative under the tensor product. I might be wrong there. Is any one of those multiplicative? I actually don't think so. I think none of them is multiplicative under tensor product. Okay. Here's an example why tensor rank is not multiplicative under tensor product, because of course the rank of a unit 2x2 matrix is 2, right? And now I take it, but I take it in 3 different directions. I take it in this direction and I take it in the other direction. I think of it as a 3 tensor, right? And I think of it, I put it in 3 directions. And when I tensor this together, actually one can show this is what is called the 2x2 matrix multiplication tensor. And lo and behold, it was a breakthrough result in 1969 that it doesn't have rank 8, but it has rank 7. But not more about that now. I just wanted to illustrate that the rank of the product of 3, which is 8, can actually go down. So it's not multiplicative. Now, what happens when you iterate the tensor product? So you could you take t and then you go to t tensor 2 and t tensor 3, right? So what I showed you as an example of tensor producting, it was I tensored 3 different ones, but I could take the same and tensor it out. So what happens then? And actually, so I tried to look a little bit on the internet. I don't know why there's this red line, and I stole some picture from this paper here. It's a Sierpinski carpet you can do. So you can take this one, and then if you tensor product with itself, right? Every of these squares up here is being replaced by the same structure, right? And so when you continue and iterate this, you get this sort of fractal like structure. And you can also do this in 3D. You get the Menger sponge. By replacing every little cube here by itself, and so thereby doing this tensor product. So this kind of brings us to the idea, which has different names, of like doing this asymptotics, of tensoring something up many times. And you can do it, you can regularize, so some people call it regularizing, sometimes amortizing and asymptotizing. I just invented up for this. So you take, and now we want to understand what properties functions have. So F here is the field. I was just confused because it was not the complex numbers. So if I have a function that goes from the tensors into the field, like the rank functions and others that I have, what I can do is I can take this asymptotic. So I can compute F of t tensor n, and then I can take the nth root of it and look at what happens when the limit goes to infinity. Now I'm not worrying about whether this limit exists or not. So F tilde somehow measures the growth of my function, because it's not multiplicative in the first place, right? So it measures the growth. So it's interesting to measure the growth of it because it's not. But of course, in the and then you can think of this: how does the rank grow? And of course, if F itself is multiplicative, like the matrix rank, then of course F tilde is equal to F, right? Because F of t tensor n is then F of t to the power of n, and then you take the nth square root, and it's equal to F. But the converse is not necessarily true. So if you have some function that is that is multiplicative on tensor products. It doesn't have to be multiplicative on non-tensor products. So if you have two different ones. So what I want to tell you now is some FaultLower theorem, and I'm sure in some way we've all kind of played with these asymptotics, have known about it. But I wanted to display it here. I think it's a very nice theorem. So let f be a monotone normalized function like the ones that we just looked at before, and let's just assume f tilde exists. Then actually it turns out that this f tilde function is sandwiched between the lion, the tensor rank, the asymptotic tensor rank, and the regularized mouse, which was the asymptotic subrank. And there's a proof for that. It's very easy. So by definition of the tensor rank, and now asymptotic, right? It's how much unit tensor I need in order to create T, but now it's because it's tensor n, okay? So that's just the definition on this side. And how much unit tensor, the unit tensor is these pointy brackets, do I get out? Now this was by definition of the definition of R tilde and Q tilde. I have this inequality of tensor of restrictions. Then I apply F to it, to all three components. I can do that. And then I use monotonicity, right? So because F is monotone under restriction, this one here will be bigger than this one here, will be bigger than this one here. And now but F was assumed to be normalized. So I can resolve actually the left-hand side because I know how F is evaluated on the pointy bracket. Namely, it's just the size of it. And the same on the right-hand side. So what I get is actually R tilde to the n is bigger than F. Of T tensor n is bigger than Q tilde to the n. And this is kind of nice because now I see immediately that the assertion is true. I just have to take the nth root and look at the definition of F tilde. So all of this, as soon as I asymptotize, somehow I have a very simple thing. I can actually see now that what I had before is true. The tensor rank is really the biggest. Everything else is somewhere in between, and the subrank is the smallest, at least when I take this asymptotic viewpoint of the world. And then, of course, what I've just told you before is that when you asymptotize, right, then your function is multiplicative on tensor products by definition, but it's not necessarily multiplicative when you take different tensors. And this raises the question of, are there multiplicative functions? And there's a theorem by Strassen that tells us, yes, there are. So there are normalized multiplicative functions. F. Oh, now, of course, I'm really sorry. I'm using F because Strassen used F here. It's not my field anymore on this slide. Which I also called F. It's actually now a function itself, like a function of tensors. And actually, there's so many of these functions that you can characterize the asymptotic rank as the maximum of all Fs. And also the Fs are good enough to characterize the lowers. And even better, the Fs are additive, but maybe let's not worry about that in this talk. And also, they actually, even better, they determine asymptotic restriction. So I should have said asymptotic here, but if f of t is bigger than f of t prime for all the f's, then actually t can be transformed, like t tensor n can be transformed to t prime tensor n. So these are kind of like the results I wanted to tell you about this field that they are. I mean, it's really a beautiful. These asymptotics of tensor functions is really a beautiful area, and I think they can give us a lot of insights into different things. And I didn't really, I guess my time is up, roughly.
You got 5 more minutes.
Yeah, so I just wanted on the last slide to flash a few results that we have done in this world that I just presented. So I wanted to kind of like use my talk to bring you into this world and appreciate its beauty in some sense. And so I've done some work in this direction. I have mostly worked with Jeroen on the subject, who is, I guess, in the audience and speaking later. We have worked together and come up with something called the quantum functionals. This is sort of like this is a bunch of Strassen Fs. So the first kind of like, sizable chunk of these additive multiplicative functions. And we've actually based them on an idea of entanglement polytopes that was grown out of work with David, who is the chair, and Michael Walter, who I guess will also speak.
He's an organizer.
Or is an organizer, I'm sorry. And this work in quantum functions we did with Peter Franer. There's some new work on slice rank. I touched upon slice rank before. Slice rank was used to understand combinatorics and certain combinatorial problems that kind of have this, have this tensor product structure built into them. And that is sort of why you can use these tools and these asymptotics tools to say something about it. Oh, this is very strange. Yeah, so we kind of show that weighted slice rank is really the kind of like the Legendre transform of the quantum functions. And that somehow, so it's here, it's from December last year. Hold on, hold on. So Vladimir was working on this weighted slice rank. Sorry, it was dropping down too late. So what is interesting about it is that our extension from slice rank to weighted slice rank allowed somehow to give a new understanding of the quantum functionals of these points. And on the other hand, it gives a new understanding of the notion of slice rank. So you can compute one from the other and vice versa. And it helps to somehow, I think, elucidate the subject. And maybe the most recent work we've been doing with Omar Fauzi and Huang Ta is on this thing called wearing rank that I was touching upon a little earlier, and to do with Comon's conjecture. Namely, one thing that we were able to show is that that symmetric restriction, so basically restriction for symmetric tensors. So like restriction when you're only allowed to use so if you imagine you have a tensor that's symmetric when you change the axes really, right? Then you can wonder what happens if I'm acting on it with the same matrix on all of them. And is that different as if I were to allow it to act with different things? And so asymptotically, we can actually show it's the same thing. And in some sense, this gives a barrier for proving upper bounds on capset-like problems, and has some application in communication complexity. So with that, I'm done. So we're hiring at QMath here. I told you a little bit about the tensor rank zoo, and we have some results we think are cool. Thank you for your attention.